we'll cover again advanced strength of materials, but now we'll cover equilibrium equations, which is a fundamental piece on how the equations of elasticity come together. Let's try to understand what we're trying to achieve, right? So why we're studying this, why is this useful? Because under applied forces, solid bodies undergo deformation. And when you apply forces to an airplane or rocket or a car, there will be internal forces acting in the vehicle that are reacting the external loads that are being applied. But there's a location in the structure that's going to be a weak point because the stress will be too high. And that could be the location where it fails. So in an aerospace design, as an example, it doesn't have to be aerospace, it could be civil engineering structure or mechanical structure. Under maximum expected loads, what we want to do is to keep that stress as low as possible below the strength of the material, but not too low, because if you make it too low, then you have a heavy structure. So you want to have a good balance where the structure has adequate margins of safety. We'll cover margin of safety in some other lecture. But to be able to understand this concept and understand how this is done, we need to understand the concepts of stress, strain, and also equilibrium equations. And I already went through this talking about the two basic types of external loads that act on the body, which is tractions acting on the surface and body forces acting on the surface. And then we discussed that there can be boundary conditions. So what is going on? So we extract a little cube. We explain to you what the cube is doing, right? Here I'm using a different notation than what I showed earlier, but it's important for you to get familiar because every book has different notation. In this case, they're using x1, x2, and x3 versus using x, y, and z. So here I have tau 1 pointed in the one direction because it's in the one phase, but it's acting in the one direction. This is tau 1, 2 because it's on the one phase, but acting in the two directions. So again, you can see here, this convention looks different from what I explained before, but I switched it so you can see that there are other notations that are available in the literature, and I want you to be familiar with that. The bottom line is that this cube here, which corresponds to a point within the structure of material, these stresses, this free body diagram, I call it free body diagram because I excise that cube out of here. And these stress components are the ones resisting the external loads that are acting on this body of material. So if you recall, you have second Newton's law that you've seen before. And it says that the summation of forces equals ma, the mass times acceleration. But if I look at a component-wise, at the x component, it says the summation of forces in the x direction equals the mass times the acceleration in the x direction. Then I can do that for the y direction and then for the z direction. So let me apply a more general form of Newton's law. If you recall, integral means summation. So what I'm going to do is to take a little cube here, and I'm going to take this cube of material. I know there's a body force acting on this volume, but also is acting on this little cube. So I'll apply the body force to that little cube, dv. Let's say is a volume dv, a small differential volume, infinitesimally small. So body times dv is the force exerted in a particular direction. So instead of looking at vector notation, I want to look at individual components so we can sum forces using Newton's law. Summation of forces equals ma in the x, y, and z. So here, I'll do it in the x direction, in the y direction, and z direction. So this vector b can be decomposed in the x, y, and z. I'll take bx, the body force, acting on the small volume, and integrate it over the whole volume. Because if I do that, I'm summing what the effects are of the body force in each of these volumes, but add it all over the place. So I'll take every little cube all across the whole volume and do the summation. Exactly what you did back in the day, F equals ma in physics. Then you have the traction forces that are acting external to the body. These traction forces can be decomposed, so they're acting in the x direction, in the y direction, and the z direction. So these tractions can also be decomposed, so they follow that the x, y, and z. So I'll take the tractions in the x direction, integrate it over the surface, because these tractions are only acting on the surface, ds, and that summation of forces in the left-hand side, we're talking about this, is equal to mass times acceleration. So here I have acceleration times density. So this acceleration can be decomposed into the x, y, and z. So I look at the x component of acceleration multiplied by density, multiplied by that differential volume, but also sum it all over the place in that body. If I do that in the x, y, and z direction, I get three equations. So we sum forces in the x direction, in the y direction, and z direction, and equate it to mass times acceleration in each of the directions. And the reason we don't have mass times acceleration here is because we're letting density to be able to vary, which could be used for additive manufacturing type materials. So now what I'm going to use Cauchy's relationship to relate the tractions on the surface to a cubic material that's just adjacent there to that surface. We know that traction equals stress times the normal to that surface, a normal that's here. So I'll use Cauchy's relationship right here, and I used it. So this equal to Tx, this equal to Ty, and that's equal to Tz. So all done is apply Cauchy's relationship. So I can then, and why I'm doing that, think about it. I'm trying to relate what you can apply physically to a system, body forces, acceleration, and tractions, which are the only things you can apply. I'm trying to relate that to what's inside of the body, a quantity inside of the body. And the only quantity that's inside of the body that I'm interested in is stresses in that cube. And so I'm using the strategy of converting these tractions into useful quantities to predict failure. And I've done that by using Cauchy's relationship, which we already covered, which is this equation here, right? The first equation here is Tx equals sigma xx times nx plus sigma xy times ny plus sigma xz times nz. So I use that here, I plugged it in to get that. And I did it for each of these three equations. And so now we will use something called Gauss theorem. Going back to calculus, you can take a surface, this is a mathematical miracle. I can take a surface integral. If I know the surface integral, this quantity here, I can convert that to a volume integral. Check it out. That's Gauss theorem. It's an amazing theorem. Think about it. It's telling us that if I know what the behavior is on the surface, I can tell you how things change inside the surface. It's an amazing theorem, physically. So go back to your calculus book, you will see that the normal can be removed, and then what you get is a gradient of that stress as it varies inside the body of material. That is Gauss theorem. How to convert a surface integral to a volume integral. You're able to do that through Gauss theorem. I'll do that for each of these three directions. And what I realize is that this, and this now can be combined into a single integral. right? Because now everything is a volume integral. So I can remove the volume integral and just say that this plus this equals this. And so I get the three equations that are fundamental to elasticity. Three equations that are fundamental to elasticity. And now I'm getting closer. I'm getting closer to determining where in the body you may have a failure. Because now I have a differential equation that can solve for stress. But the answer is I'm still not there yet, because if you notice, how many unknowns I have? I have 1, 2, 3, 4, 5, and 6. But I have 3 equations and 6 unknowns. So I'm not able to solve it yet, but I'm getting somewhere. I'm getting somewhere. We'll get there very, very soon. And hopefully that was clear how we got to these 3 equations. I'm going to do it differently now using a different method. But if we go there, I want to make sure the material is well understood. So I'll continue here. So what I have now is, I'm going to derive this a little bit differently now. So what I'll do is take a cube of material again. And what I'll do, for example, let's focus on sigma xx plus partial of sigma xx dx dx. I'll take a differential volume. On the left-hand side, I have sigma xx. On the right-hand side, I'm going to take a differential volume with a small addition of sigma xx partial dx dx. So I have sigma xx plus this, and I'm going to do that for every single one of this. So this differential volume contains the same approach of adding a small amount of sigma on the other face, from the bottom to the top, from the left to the right, and from the back side to the front. And what I'm going to do, I'm going to sum forces in x directions only. So if I do force equilibrium in the x, y, and z directions, then if I were to do the x direction alone, let's look at that. So I have sigma xx here. Let me circle it so you can see it. Sigma xx. This height here is dy, and this is dz. So the force due to sigma xx acting on that surface times dy and dz is the force in the x direction, but it's minus because it's going in the opposite x direction. I'm summing forces in the x direction. That's what I'm doing. Okay. Now I'll focus on the forces on the right-hand side, which is this one right here. So that's this one. Same thing, but now it's acting on the positive side. I have sigma xx plus partial sigma xx dx times dy, which is this height, and this edge here is dz. So that's that. That's the area of that surface. And stress times area gives you force. And that's the force exerted in the x direction as well. But that's going to the right because this arrow is pointed to the right. Now I'll keep summing forces. And what you see here is I have this one on the bottom. That's this one. And that stress has to be multiplied by the area, which is dz and dx. And that's what you see there, dx and dz. And that gives me a force moving to the left, which is y is negative. Now I'll add to that the one at the top going to the right, which is this one. And you see that here. That one has an edge that's dz, and this edge is dx. That's why you see that there. So stress times area gives you force. That's what I'm trying to do here. Okay. And then I can repeat the same process for the remaining edge, which is this one here. Sorry, for the remaining face, which is this one here. And I won't repeat it because I already did two of them, but the process is the same. And the one we're talking about there is this one here, which is this one here, moving to the X direction, and the one in the backside, which is not drawn because there's too many arrows everywhere. But I think you follow the process so far. And what you notice here is that this sigma xx cancels with this one because that's multiplied by that. So this cancels with that, this cancels with that, this cancels with that. And then you have the body force in the X direction, and it has to be multiplied by the volume, dV. So when I do that simplification, I end up with this equation here. And you notice that now I have dx, dy, dz in every single one of them. And very similarly, as I said before, because the d volume is not zero, what's inside here has to be zero. I didn't put acceleration terms. So in this case, I did it statically. So that's why these are zero, because I'm not assuming acceleration in this example. So I've shown that in the X direction, we get the same answer as previous. So now let's look at why the stress tensor is symmetric. There's a way to show that using the conservation of angular momentum. So basically you have these forces that we were discussing earlier. So these forces we're discussing earlier. But now if I take this position R to that point here, R, position vector R, and I cross it against the force B, I get a moment. And so I'm going to do that for every single one of the forces that I have in the system. So I'll do it for this, I'll do it for this, and I'll do it for that. So once I do that, I can prove that the stress tensor is symmetric, but the proof is not easy. And I proved that in a more advanced course, in a graduate level course. Instead, let's just make it easier. So I know that sigma yx is acting on this face. We know that sigma xy is acting on this face. We know that sigma yx is acting on this face. And sigma xy is acting on that face. What I'll do, I'll sum moments about the center. That's one approach. I can also sum moments about this point so that these two cancel out. If I sum moments about this point, what I get is the sigma xy, which is acting along this face, which has area, it has a depth of A. So this edge is A, the depth is A, sigma xy times A squared has to be equal to sigma yx A squared on this edge. A squared cancels out, so sigma yx has to be equal to sigma xy. If I sum moments about this point. If I sum moments about the center, then I get this equation here, but very similar answers. And I'll get that the stress tensor has to be symmetric. I can repeat this process for all other phases and prove that sigma xz equals sigma zx, and prove that sigma yz equals sigma zy. So the stress tensor is symmetric, meaning that these off-diagonal terms I had, the off-diagonal terms are zero, are symmetric, is what I meant. So sigma yz, yx is equal to sigma xy, sigma zx equals sigma xz, sigma zy equals sigma yz, and that's the proof for that. So let's apply it with an example. So sigma x is given as this, sigma y is 0, and tau xy is this amount. All the other stresses are zero. We want to show that this system is in equilibrium. So partial sigma x y xx partial x partial tau yx respect to y is zero if I were to use this equation here. But these stresses do not exist because I told you these are zero. So simplifying things quite a bit. And there's no body forces according to the Parallel statement. For no acceleration or body forces, show the system's in equilibrium. You can see here that the partial with respect to x, you get 3py divided by 2c cubed. And then for this one, you get 3py divided by 2c cubed, if you take this partial here. And that's exactly equal to zero. And then you can see that tau xy has no x's. So therefore, the partial of tau xy respect to x is zero. Partial sigma y respect to y is zero, obviously, because there's no sigma y is zero. So this system is in equilibrium. This is an exam problem from a previous year. The following describes the stress distribution in a body. So it gives you the stress components, all six stress components. Remember the sigma y z is zero, but sigma zy is also zero because the stress tensor is symmetric. Sigma xz equals this amount, but sigma xz is also equal to sigma zx. I'm using tau here, but they're used interchangeably in the literature when we refer to shear. Finally, sigma xy equals sigma yx because of the stress tensor being symmetric. Sigma xx, sigma yy, and sigma zz represent the components of stress normal to the surface of a cube. While these components are tangential to the surfaces of cube, causing the cube to distort. It says to determine the body's force distribution required for equilibrium and the magnitude of this resultant at this point in the system. So then I'll use these equilibrium equations. I have zeros on the right-hand side because there's no acceleration, or the problem statement does not talk about any type of acceleration being applied. So this is zero, no accelerations. I'll plug each of these quantities into these derivatives, and I won't do this step by step because you know how to take derivatives. I'll do just one of them, for example, partial sigma xx with respect to x. There's 3 times 3, 9, 9x squared. That's what you see there. And then the rest of them is the same process. I'll plug it in. And what the problem step is asking me what is the body force distribution, which is this fx, fy, and fz. So I have to solve for these values here. So I solve for fx and fy and fz from this equation by isolating it and moving everything to the right-hand side, except for fx, fy, and fz. And then I plug in the values for x, y, and z. And when I do that, I get what f is. Notice that it has units of force per meter cubed because it's a body force, and body force is per unit volume, as discussed earlier. Same for fy, and same for fz. To get the force resultant, all I have to do is take fx squared plus fy squared plus fz squared to get the magnitude. And obviously this tells you the components in each of the three directions, x, y, and z. And that's the magnitude. This example comes from my own book. I provide the following problem statement. I'm asking you to find what A, B, and C is for this system so that the body is in equilibrium. Notice that I'm telling you to ignore all body forces and there's no accelerations. So I'll go ahead and plug in each of these things into the equilibrium equations. There's three of them, 1, 2, and 3. There's no body forces, so that's zero, no acceleration. But I can plug that in, and I get that 4x times a minus b is what I get. But this needs to be equal to zero because the body is in equilibrium. There's no body forces or accelerations. So for this equation to be true, a has to be equal to b. The second equation, we plug all the expressions in and take the derivatives, and we find that 4y times minus b minus c has to be equal to 0. But that's true for every point in the body, so y cannot be 0, every single point in the body. So b has to be equal to z. And it turns out that the third equilibrium equation is satisfied exactly. So the conditions are that a be equal to b and b be equal to c. And if that is the case, then this system is in equilibrium. We have other coordinate systems. So these equilibrium equations I showed you here are for our Cartesian coordinate system. If you go to a cylindrical or polar system, which is very convenient for studying cylinders, disks, wedges, curved beams, we'll see that in this course, then you can do equilibrium for a cylindrical system, for example. And in a cylindrical system, you have that the z direction is your revolution axis. The radial direction is going away from the z direction. And then theta direction is perpendicular to the r direction and is called the tangential direction. A point in this body of material can be described by coordinates that are in the z direction, the height of that point, the radius away from the center of axis there, revolution axis, and theta, which is tangential to that point. So, for example, a theta equal to 0 will be a point along the x1 axis, for example. A theta of 90 degrees will be a point along the x2 axis. And the stress components are defined very similar as before, where sigma r is perpendicular to this surface, and that's a normal to that surface, sigma r. Makes sense, is r face in the r direction radially out. The other components of stress are tangential, and there are shear stresses. Sigma theta theta here is acting on the theta face in the theta direction, and so forth with the other components. The equilibrium equations are a little more complex, but nothing to be worried about. The equilibrium equations look like this, where Fr, F theta, and Fz are the body forces that correspond to the radial, circumferential, tangential, and the z direction. So this allows you to study spinning disks and other things like that, and we'll be looking at that later. Then there's a spherical coordinate system or polar coordinate system, where a particular point in the system in the body is defined by the theta, phi, and the radius direction, which is measured from the center or origin of this coordinate system. And what you see here is, for example, that sigma rr is perpendicular to this surface, and that makes sense. And sigma rr is one of the components here. Sigma phi phi can also be defined as this one here, and then sigma theta theta can also be defined, which is this one here. The equilibrium equations look a lot more complex, and r here is the distance from the origin, but the equilibrium equations are given here, and you can actually study that by applying it to different problems.